Thank you. So maybe before I start this talk, I want to throw three caveats. The first one is that there's not a single pseudo-Boolean constraint in my talk. Just to be clear, everything I'm saying, I'm going to say it for classes. It works exactly the same for pseudo-Boolean constraints. The second caveat is that this title is the same title of a paper that we got accepted in SINASC. It's in archive, the submitted version. Soon there will be an updated version with a lot of extra stuff. But the talk is not about that paper. The problem that I have is that paper, so the research leading to that paper, it has material for a bunch of papers, and I had to select a part to just take apart and be able to submit it. Against my will, so it doesn't count as salami slicing. And the problem is that from that paper, it's not really clear what I'm trying to do because I had to splice it. So this talk is all the quiet part of that paper said out loud, where I'm going to explain where I'm going with all of it. Yeah. Okay, let's go. So, this problem has been living rent-free in my head for a while. I'm going to take 3 formulas, and they're going to all be unset, and they're going to be really hard formulas. So the kind of formulas where you're going to throw everything that you have in your solver at it. And they're all unsatisfiable, but they're over the same variables. That's going to be critical. So one thing that I can do to make another formula even harder to satisfy from these 3 formulas is I take 3 fresh variables, I disjoin them with the clauses, and of course this is not CNF anymore, but what I do is I write a variable in every clause in each of the formulas. And then and then I add just this clause negating every of the extra literals I have introduced. This is still unsatisfiable, right? And now imagine that I have a solver that is very smart, that doesn't exist yet. It may one day exist. And it's a distributed solver. So what this solver is going to do is, oh, I see what you did there. I know how you did this. Okay, let me split apart this formula into 3 pieces. Send it to 3 different solvers. And there's some delay here. Okay. And I'm going to send it to 3 solvers. And the 3 solvers, of course, these 3 formulas by themselves are satisfiable, but eventually if you run CDCL, you're going to learn the clauses U1, U2, U3. And now these are fresh variables. So, you know, so far I have done nothing satisfiability preserving, it's just pure CDCL. So I can take these 3 clauses and conjoin them with, resolve them with the not U1, not U2, not U3 clause, and get a contradiction. Good. And
so far it's cube and conquer.
So far it's cube and conquer. How do I get a proof for this? Well, we know how to do this. There's root proofs that are generated by each of the 3 CDCL solvers, and I'm going to have, after those 3 parts, I'm going to have a little proof that just joins these 3 proofs and the extra clause to obtain a contradiction. Good. And now what I'm going to do is like, okay, this is cute, but these are really, really hard formulas, so I want to do symmetry breaking here. And the problem, okay, okay, thank you. The problem is I'm going to have 3 different symmetries in each of the formulas. And remember, these formulas, they are over the same variables, so the symmetries are not going to extend to the other parts of the formula, right? Okay, so I can do symmetry breaking. Okay, I'm doing this. I can do symmetry breaking there. I selected just one symmetry, very small symmetry, so that rat doesn't show up. And then I can introduce these symmetry breakers. They're all rat clauses, so this is a very, very simple case of redundance-based strength, right? And this is known how to do for single symmetry. It's a simple symmetry. Okay. Now, here's the problem. Now I'm going to do the same procedure. I'm going to learn these three clauses, U1, U2, U3, and these were so I have learned them after introducing a symmetry breaker. But those clauses, they still follow from the formula. In fact, before I introduced the symmetry breakers, I was assuming that my CDCL solver was super fast, and I derived the same clauses. So there are still consequences. So in principle, I should be able to still merge the proofs and do the same thing as I did before, right? But I can't. And the reason is that there's this phenomenon that the Maranhel and Benjamin Kiesel call interference. And interference basically means you have a proof of some statement, and you have another proof of some statement from two different premises. Now I conjoin the premises. I know that the conjunction of the conclusions should hold if they follow, but the proofs still cannot be merged. So the conjunction of proofs is not a thing in systems that present interference, right? And that boils down to what DRAD proofs. And when I say DRAD here, I'm talking about DRAD, DPR, DSR. I'm talking about VeryPB. What these proof systems are doing. Okay. So what are the semantics of a DRAD? So if I have a proof of a formula G from a formula F, a DRAD proof, what I'm really proving is not that G is implied from F. What I'm proving is that if I have an assignment that satisfies F, then I know how to transform that assignment into something else that satisfies G. That's a type. So the second one should be a G. Okay. And what is this mute transformation? Mute is a sequence of operations, and they all have the same structure. It's if my model or my assignment satisfies some condition, then I'm going to replace the assignment by the assignment with some substitution applied to it.
So just to make the connection, Adrian, like these omega witnesses that we use to patch up.
I'm writing them as sigma, but these are the same. Okay, and okay, so every time that you do substitution redundancy, which is what in VeryPB is called redundance-based strengthening, introduces a new mute operation in this sequence. So it's if I satisfies F, then I have a sequence of transformations, and after that, then I should satisfy it. Yeah. Okay. So now let's see what's going on in here. I have a proof pi1. That's the same proof pi1 from before, and I'm showing that from U1 or F1. I can derive U1 or F1 together with the symmetry breaker that I introduced, right? And from there, eventually, I derive U1. So semantically, what is going on here is that I have proven that if I have a model satisfying U1 or F1, then I have a transformation that maps that into another assignment, and the transform assignment satisfies U1, right? And similarly, for the other, right? So mute here is if I satisfies the symmetry breaker, the negation of the symmetry breaker, then is replaced the assignment with the assignments with the same assignment where I have swapped x1 and y1, right? So just apply the symmetry to the assignment.
Is G in your is that just a single clause?
Sorry?
Is that
where F entails G? Is G a single clause?
Where F entails, sorry.
Just in the very above, under what are DRAP proofs really doing?
For
G is just a clause.
G, no, G is a whole formula, right? Yeah, exactly. Thank you for pointing that out. That's going to be super important in a moment. Okay, so now I have the same process for every of the other parts of the formula. And here's the problem. In these mute are different, which means that I cannot really merge the three proofs, right? I haven't proved U1, U2, U3. I have proved that for the after transformation 1, then U1, after transformation 2, then U2, after transformation 3, then U3, right? In order to merge them, what I am going to need is this, right? I'm going to need just a second, that U1, U2, U3 follow from the assignment, right? Not from the assignment after transformation.
In this example, you could really construct like the counterexample where you have the same model for the three formulas that don't satisfy U1, U2, and U3, and you do symmetry breaking. Now you get only models that force U1, U2, and U3, and then you get global ansat if you're just blindly merging the proofs, right?
Yeah, exactly. That's a problem. That's why you cannot do it. In principle. Yet, because U1, U2, U3 are fresh, I know I can do it. Right?
But so can you not because they're fresh for each sub part of the formula you can add the clause just U1 by RAT because you know U1 is fresh. And then in the second formula you add U2, and the third formula you add U3, and now you get a global, and you can't merge it, but
yeah, I cannot.
Yeah, so
well, I mean, you could. Okay, that's what you're saying. I mean,
it's a very simple counterexample.
Okay, yes, in this case, you could probably massage things so that it will work, right? But I also think that the point I'm going to make is a lot wider, right? It's more like, okay, I have two solver, I have a distributed solver. They do some sort of, satisfiability preserving shenanigans, and eventually I get conclusions I want to be able to merge, right? Like you want, sure, you want in this case is you can do writing here, but what if I learn any other literal that is not affected by the symmetry, even if the same literal appears on the other clauses, right?
I mean, my counterexample is actually saying that you can't merge proofs, right? So
yeah,
I agree. Totally agree.
Sure, okay. No, I mean,
yeah.
I just a lot in this. It's cleanliness, right? Okay, so all right. Solution one that I could think, why I'm trying to fix this situation. The solution one, okay, why don't you break the symmetries before splitting? That's not even sound, right? Because the symmetries are symmetries for F1, for F2, and for F3, but they might not be symmetries for the whole form. Again, they're over the same variables. Solution two, we could allow nesting DRAG refutations, and actually, I don't know if in a subproof by contradiction in VeryPB you can actually do so strengthening steps.
No, that's just a design choice.
That's a design choice. You could do it. So that
yeah.
So the idea is, well, I mean, I'm trying to derive U1. So what I could do is negate U1, and now the only thing I need is a refutation. And because refutation, whether you do, we're talking about satisfiability preserving proofs. So if I'm only needing to derive a refutation, then this is fine to derive, right? I don't care what kind of satisfiability shenanigans, satisfiability preserving shenanigans I do in that implication. Problem with that, what if instead of just deriving U1, I need to derive 3 clauses? Well, now I find myself in the situation where, because the derived refutations need to be nested, they need to be independent for each clause. And now I find myself in the situation where I need to introduce the same symmetry breaker 3 times, despite the fact that I know perfectly that nothing has changed, that I can still do this. Basically, that this is a forced problem by the restrictions of the proof, right? There's a side problem, which is if you do this, then you need to know in advance that U1 will be the clause derived by the solver. This is not a huge problem because you can always include in the semantic, so include in the some sort of instruction in the proof system that says, yeah, when you read this, please go back and insert this nesting or whatever, right? So this is the syntactic problem. Okay, I want to solve this problem for good. Okay, the thesis of this talk: accumulated formulas are not your friend. What do I mean by accumulated formula? This is the formula that is accumulated through a Dirac proof if you're in a Dirac setting. If you're in very PV, this means core and derived clause, core and derived sets. And of course, dominance is completely dependent on these 2 sets. I disagree. We'll come to that. Anyway, the mutation operator. This is what well, we can call it mutation. Martin Suda and I like to call it Fefe, because what it does is it takes some state of reality, checks if it's true, and if it's not true, then it patches some light so that it becomes true, right? So anyway, there's this notion here, which is this would be the mute transformation that I have presented before. And yeah, I had this idea of, okay, I have some transformation that I can apply semantically in the meta theory to my assignment to transform it into another assignment. Cool. Why don't I just have that at the syntactic level? So why don't I have that with the clause? So what you get is basically, okay, instead of clauses, I have clauses preceded by a number of mutation operators. And because I have made that explicit, now I can have a calculus for it. And the moment that I have said calculus, you're already imagining like, oh, this is going to have 7,000 rows. But anyway, let's think about what could we get with it. I have a formula, right? And F is going to be the formula. So this conjunction of 3 big formulas plus the extra clause with the negations, right? And this is how I could imagine writing it. So I take F, then from F I can delete a bunch of clauses until only U1 or F1 is remaining. Then we can introduce with this mutation operator, we can derive U1 or F1 under the mutation operator. And I write there by substitution redundancy. Wait, but I haven't introduced anything. Right. So remember when you have substitution redundancy that you need to prove both the formula and the clause under substitution, right? Well, this is the part where you prove the formula under a substitution, right? So what I have derived here is basically that from U1 or F1. Oops. Oh, this is that then. From U1 or F1, I can derive U1 or F1 after the mutation operator, after the mutation operation. And now, additionally, I need to derive the symmetry breaker, right? These are the 2 parts that are contained in the definition of redundance-based strengthening, right? So the first one derives F under the substitution. The second one derives B1 under the substitution, and B1 is the symmetry. Okay, by a bunch bunch of resolutions, I end up deriving U1. And now the thing is, those resolutions have happened after the transformation. So of course, they contain it after the transformation. And now by cleanliness, and this is a notion that I think that Katalin Fachekas came out with it, and is quite used in incremental solving. By cleanliness, I can derive U1 before the substitution. And what cleanliness is doing here is like, oh yeah, so here you're saying if I satisfy something, then apply the substitution, or otherwise don't apply it. But that substitution has nothing to do with U1. It doesn't touch it at all. Therefore, U1 already held before the transformation. You don't need to worry about it.
If we want to translate back to very PB language, you'd say this works if you promise to me you maybe did strengthening in the proof, but U1 was never in the witness of any substitution.
For example. And I can do that for the three subformulas, right? Right. So now I have derived U1, U3 with no mutation operator. And here's the problem. Okay, I have deleted the rest of the formula, right? So in the first line, so from F I go to U1 F1 or U2 F2 or U3 F3, and at that point I have deleted the clause not U1, not U2, not U3, right? This is the one I need to resolve. And I don't know how to recover. So let's assume I can recover by some arcane magic. And then it's just a single resolution, well, 3 resolution steps, and I have reached a contradiction.
Are you imagining all 3 of these columns here in the same proof right now?
Yeah, so imagine that at some point I'm able to just have a nested proof of sorts.
So in the first step, did you delete everything from F?
Yeah.
Except
for
U1 and
those-
F1.
Exactly.
So how do you get U2 and F2 back? Or F2?
Yeah, my argument is, okay, very PB is not able to do this, right? And yeah, the point of this talk is maybe it's true. Okay, there's a problem. It looks very simple, right?
Just one thing: if your witness do not touch this clause U1, U2, U3, then you can just never delete it. You just keep it, and you still have.
Oh, in this case you could. In this case you could, right? But then again, like my argument is yes. Like for every single case that I can give you, you're going to say like, oh no, but you could just take the very PB proof system or the DSR proof system and do things in a sneaky way so that it works. Sure. And every time that someone comes up with a new method, you would need to sit down and think of it. Okay, so this seems to work, but there's this some arcane magic there, right? Okay, why this is too simple? Why doesn't it work? Like, no, seriously, like, why cannot we just do this? Like, you have F at the top. Everything that I have derived here is a semantic consequence of it. I have not used satisfiability preservation anywhere. I don't need an accumulated formula to do it at all. So, okay, yeah, the arcane magic. What is the arcane magic? This is a primary. I don't need an accumulated formula. I don't need to worry about deletions anymore. Think of resolution. In resolution, you everything that you derive through the proof tree or through the proof DAG is a consequence. Sure, deletions, you could write deletion instructions, but deletion instructions are just something for the checker not to choke up on the formula, right? But I can just take any subproof in the proof checker and check it independently, right? So, okay, we could do this, right? We could just forget that we have accumulated formulas or configurations or whatever, and just operate on the proof with the idea that if I have ever derived something in my proof system, then that holds. So that follows from the premises. But of course, that breaks some things, or at least it looks like it, right? So I'm going to spend some time convincing you that nothing is broken and a lot can be gained by doing that. So, okay, trimming. We just heard talk about trimming before, and so here's the problem with trimming. If you have a resolution proof, or root, poly lines, whatever, then trimming that proof is easy. You just traverse back the tree, right? But then you have redundance rules and dominance rules, and these rules, the whole formula is affected because they depend on an accumulated. Okay, and this is part of some work that I published 2 years ago, but I think that the point of that paper didn't get me. So let's see. I have a formula, and from that formula, I'm going to introduce a symmetry breaker. So I'm able to derive the formula and the symmetry breaker under a certain transformation, right? And this is, again, consequence. This is not just satisfiability preserving. There's I have an assignment, then I can transform the assignment. No, this is full implication. What does this check require? So, for example, by strengthening dominance-based strengthening, what it parses these 4 checks that I have written there, and I write applying a substitution. I write it as a line, not as an arrow, but I think that the meaning is. These are the conditions that appear in the very PV system. And now here in the left, I have fewer clauses. In principle, I could use all of it, but let's assume that well, I have analyzed my subproofs, right, and my whatever very PV did. And here's the clauses that I actually needed for those implications, right? So instead of using all of F to derive C1, I only use C1. And for C2, I only use C2. But for C3, I actually needed C3, but also C1, right? Okay. So now the second thing that I'm going to do is take F together with the symmetry breaker and just end up deriving a contradiction. And let's assume that this is very easy. It's just if you conjoin C1 and B, then you get a contradiction. I don't know. I don't even know if there's an reasonable instantiation for this, but this for the sake of the argument. Okay, so let me try to rewrite this condition over here in my language. In my language, this is written like this. So from C1, I can derive C1 under the transformation. I can do that for each of the other items, right? Okay, and now let's trim this proof. So I'm using, I think, the first method that you explained, right? So I'm going to start from the bottom, and I'm going to traverse the proof backwards, and I'm going to be marking the clauses. Now with in this case substitution redundancy. So I start there. Now, okay, bottom had as antecedents C1 and B. So C1 and B should be marked, but they're marked under the prefix of the mutation prefix that I'm using, right? Okay, so now I go to these implications in the left. I look for the first one is B, right? The first one I'm going to do is C1. So I look for this clause, look for it here. I mark the antecedent, right? So C1 should be marked. The other one that I have here is B under the mutation. I look for it here. Oh, this one dependent on C1 and C2. To try to do this, with DPR trim, it will now go into some fixed point behavior that is completely unnecessary, but if you want to express the proof as a PR proof, then you need it. But anyway, from my side, I'm done. I have marked C1 and C2. I know that that C1 and C2 are the only things I need to prove the contradiction. C3 is unnecessary. Good. So trimming seems to become easier if you do this. And of course, this was known. This is the weak substitution redundancy that I published a couple of years ago. It's not clear how to quite merge it with VeriDB. And the reason is this accumulated form. Let's see what other things are here. Okay, so all right, so if I'm going to get rid of the accumulated formulas, one thing that we should care about is, okay, what is happening with satisfiability? Because now I don't, like, okay, what happens when I delete a clause? And in the end, I find a model only for the clauses that remain in my formula. Well, let me give you a different perspective on what it means for a formula to be satisfied. So I have 4 clauses, and I'm going to first delete C1 by this substitution. If you're into this, this is just a block clause, so I can do that. Then I'm going to delete C2 by another substitution, also block clause, C3 by another substitution. In the end, I only have C4, and at this point, it's like, okay, let's stop playing cat and mouse, right? This is this is satisfiable. Here's a model. Okay, so when these deletions I have performed are something called redundant clause deletion, and the argument behind it is I know how to transform models of F without the clause into models of F with the clause, right? What is the transformation? It's a mutation operator. It's again the same thing. Good. Okay, and what is satisfiability? Satisfiability means if I have a model of top, what is a model of top? Any assignment, right? If I have any assignment, I know how to transform it into a model of F, right? Okay, so here's what I'm thinking. I can express satisfiability proofs using exactly the same mechanism, this transformation-based mechanism, right? So I can have a proof that starts with nothing, with no premises. And then I apply the substitution sigma 4. And from the substitution sigma 4, C4 is an act, so it is a tautology. Because that's what it means to be satisfied, right? Okay, and then from C4, I know that I can extract, that I can conclude C3 and C4 because of the condition by redundance, the clause deletion, right? So I can hear about this from C4, C4, I'm deriving mutation C3 and C4. Turns out that whenever you can do that, you can wrap the proof under a transformation itself. And then you have this, and then you have a transformation from any assignment into an assignment satisfying C3 and C4. You can do this recursively, and what you get is, okay, satisfiability just means I can prove the formula under a transformation from absolutely nothing. This is related to the specifications in pre-orders with extra variables. The specification did something like that, the derivation through redundance from the entity. Okay, incremental solving. So let's see, this is the same formula that I have just used. And now what an incremental SAT solver might do is, well, I'm going to insert C5. C5 is not Y or not C, and this is clean on sigma 1, sigma 2, sigma 3. Okay, this cleanliness thing is a bit weird. What this means is if I have something satisfying, so if I have an assignment satisfying C5, then I can make the other way around. If I have an assignment satisfying C5 after these transformations, then I can revert the transformations and obtain an assignment satisfying not Y or not C. Okay, so okay, I have that implication by cleanliness, and now I can just try to solve this. I add it to my class set, and now I find a satisfying assignment, and I do the same trick that I just did. And what I have is that, well, from the empty set, I can derive under, by sigma 5, I can derive C4 and C5. And then from there, oh, okay. Apparently forgot to write this. So from the empty set, I can derive C4 and C5. And now from C4 and from C5, I can derive all the other clauses under mutation prefix, right? Okay, so that's a satisfiability proof for me. Okay, so I'm going to rush through this. The take-home message is you can do this, right? With incremental solver. Okay. What's in the box? So the box is a pun, right? Because this goes through model logic. This idea that I have expressed that if you have a transformation and then some premises under a transformation, and you have a proof from those premises of something, then you can derive that under the transformation too. Okay, so this seems to solve a few problems. What about dominance? It works. It needs a huge iter through model logic. And this is related to something from the 70s called propositional dynamic logic. This is something that theoreticians are very interested in model logic. They're not interested in practical solving at all. What about deletion in unsatisfiability proofs? They just become performance annotations for the solver. And this is fine, and it works. How many rules do you need? Not many. So what I have done is basically trying to express all these constructs with mutations and so on, and try to have them as a separate. Trying to have room extended to operate over those, even though those are not going, those constraints are not going to live in that form in the checker, right? Wouldn't proofs be very long? Not really. This is a matter of proof engineering. Are the text complex? Not really. And also, these proofs can be parallelized because I don't have an accumulated form. This is new redundance rules. Yeah, a lot. So since we need to wrap up, I'm going to go very quickly through how this works. Yeah. What is an assignment? An assignment for me is going to be just a mapping of variables to bits. You might call that the memory state. What is a transformation? A transformation is going to be a program, any program. And my programs are going to be partial. They're going to be non-deterministic. I'm going to do all sorts of shenanigans. I have some Greek semantics for it. And you have this necessitation theorem. This is coming straight from model logic. It doesn't depend at all on what kind of programs I'm defining. It's from the meta theory. It doesn't. I don't need to be careful with how I'm defining my program so that this holds. This gives you parametric lemmas right out of the box. So this that someone was debating a few days ago. Well, I have a proof from F, I have derived G, and I would like to just take the same proof. This proof was very complicated. I would like to just have a proof of F by sigma, maybe because I have replaced some variables in here, and I would like to get G of sigma. Okay, but this substitution, this is a program too. right? What do I need to do here in a proof checker to prove that this is correct? Just write the name of this proof. That's enough. Okay, so quickly, these are the basic programs that I'm dealing with. I have assignments that are basically the same as in VeryPB. I have sequential composition. So I can compose transformations with transformations with transformations. I have non-deterministic. So I can choose non-deterministically between two transformations. I have assertions, non-deterministic repetition. This is dominance, by the way. That's the loop in the proof of dominance. I have concurrency, and this sounds like, why the hell would you need this? It's super useful. And I'll give you an example in just a moment. I can run a SAT solver inside my proof system. And that's actually a transitional relation in the way that Simon just mentioned in the previous talk. I can have branching, I can have while loops, I can have a program that blocks, I can have a program that is completely non-deterministic and just garbles up the memory every step. I can have universal quantification. Okay, so I have now conditions to define what a proof of unsatisfiability is. I have conditions to show what a proof of satisfiability is. Safety properties, which you might be very interested in hearing about, because planning and model checking, they're not that far away. Liveness properties. Where are we at the moment? Okay, so we have a logical framework. In this logical framework, trimming, distribution, incrementality proofs, parametric proofs, all of these works right out of the box. You won't break this by adding new rules. This is not like carefully constructed so that nothing breaks. This just works. This is a paper that is already published. Well, it's already accepted. You can check the submitted version in arXiv. You have a proof system that basically simulates all of substitution redundancy without interference at all. Can have proofs to handle dominance in the way that VeryPB does it, without interference or accumulated formulas. Auto-proving is only partially possible, and here by auto-proving I mean group-like proving, but in the VeryPB case it works. And I'm ironing some kinks out so that dominance can take full generality, and that means I can have while loops of whatever the hell I like with whatever termination. And nothing is implemented yet. So if you want to help me with any of this, because I'm doing all of this alone and it's a lot, please write to me. I will be super happy to collaborate. Thank you.
One or two quick questions for Adrian.
Yes.
For trimming, why, if I don't want to trust you, like when I don't trust Matthew, and I still want to try merge things that should not
Okay,
that should be hard.
so now you're not restricted by having an accumulated form.
Yes.
I mean, if you don't want to trust the proof, then you're not trusting the proof. But you can still use the framework, right, to decide how you're going to trim it.
You said nothing's implemented yet. Do you
Yes.
have like some ideas for what a maybe
Yes.
readable format would look like?
Yes, in the paper there's a preliminary version. The gist of it is I try my best not to need to write the whole prefix for every constraint, and it works by having context.
Okay, so Adrian again.